Hello, and welcome to our final NLP plus CSS 201 tutorial of the semester. I'm Katie Keith. I'm a postdoc with the Allen Institute for AI, and I'll have my co-organizer, Ian Stewart, introduce himself.
Hi, everyone. Thanks for coming. My name is Ian Stewart. I'm postdoc at University of Michigan, and I'm excited for this to be kind of the last tutorial of the semester with Neha, and I'll let Katie introduce her.
Yeah, so our host today is Neha, who's a current PhD student at the University of Massachusetts Amherst. She has an MS in computer science from Stanford, has also worked at Google as a software engineer. And today she's going to be telling us all about word embedding. So without further ado, I'm going to let Neha take it away. I will say, if you have questions, please post them in the chat. Ian and I will monitor that, and there'll be some natural pauses during Neha's presentation.
Awesome. Thank you so much for the introduction. And now let me just figure out how to play this. Second. There we go. Okay. Hopefully Keynote will be kind. And I can also just post in the chat the slides in the notebook. So thanks everybody for joining today. As Katie said, I'm a graduate student at UMass Amherst, and although currently I do research in discourse structure and trying to understand peer review discussions from that perspective, in a previous life I did work on word embedding stuff, so I'm kind of excited to present sort of a whirlwind tour of mixed bag of mixed metaphors today, with a lot of work that I really like. I just want to check that I'm not muted or something. Okay. So this, I just want to say at the outset that this is a little bit unusual for from what I've seen of these tutorials. There's a lot of slides, and although I've shared a notebook, a lot of the topics that we're going to look at need a lot of time and memory to run. So you might be really disappointed if you try to run things in the collab, but hopefully I hope you like my slides and the links to the papers that are in there. Okay. So just as an overview, some of the goals for today are just to revisit the mental models that we're supposed to have around word embeddings and learn about possible pitfalls that you might encounter when you're using word embeddings in your research. And the way that we're going to do that is by looking at word embedding analogies, talking about how different phenomena and lexical semantics affect word embedding behavior, and also by looking at factors that affect the stability of word embeddings. But most importantly, we are going to talk about how to mitigate the effects of the problems these things can cause in your work. And at the risk of sounding a little bit negative, we can also talk about some of the things that we won't discuss with pointers to other places that do discuss them in great detail. So we won't talk about BERT, but there's already an excellent tutorial on that. We won't talk about how to train word embeddings, but you can follow Sperling and Rodriguez for that. And we won't talk about comparing word embedding models. And finally, most unfortunately, I don't really know a ton about word embeddings in languages besides English. So a lot of this work is going to be based on English. Some of it will generalize, but I just wanted to say that at the outset that I'm not claiming that this is true. Everything is true for all languages. So let's do a quick recap of stuff that's probably familiar to you, but just, to get us all kind of on the same page. So what exactly are word embeddings? They're representations of words in text. They take a form of a vector in RD, so a list of D real numbers where D is the dimension of the vectors. And they're learned by a class of algorithms, including Word2Vec, GloVe, and FastText and others, but Word2Vec and GloVe are the ones we're going to focus on today. And the idea is that these vectors represent the meaning of a word, and that comes with a couple of caveats. So first of all, when we say the meaning of a word, it's the way that it's used in a corpus. It's not sort of some Platonic ideal of the meaning of the word. And that can work both in our favor and against us, and we're going to look at both of those outcomes in this talk. And the second caveat is it represents the meaning of a word if we accept that the description of a word's context constitute its meanings. And there might be linguists and philosophers who don't always agree about that, but we are going to take that as a given for the rest of this talk. Great. So we also want to talk about distinguishing the two different uses of word embeddings, and this terminology comes from this excellent paper by Antonyms and Minot that we're actually going to look at in more detail later in this talk. So the first type of use of word embeddings is downstream-centered word embeddings. And this is when word embeddings are manipulated to form phrase, sentence, even document embeddings. And those are used in models like sentiment analysis, summarization, and all kinds of deep learning things. And then those are also kind of the precursors to things like BERT and other like large language models and contextual embeddings that you might come across. That is not what we're going to be talking about. We're going to be talking about corpus-centered uses of word embeddings. So the idea here is that the text is sort of a product of the mental model of the author, and we can study word embeddings as a representation of that mental model. So it's kind of a way to study the people who generated the text. And some examples of that you might have seen are like diachronic word embeddings, or like semantic projection from like this geometry of culture paper that's been really popular. Just to give a sense of what exactly corpus-centered research can look like, I just want to mention as an example one paper. So there's a paper by Gennaro and Ash that I guess just came out this year. And they're talking about emotion and reason in political language. So in the kind of space of word embeddings, they sort of find a dimension between emotion and cognition. And using that dimension, they describe how different participants in US Congress speeches behave. And they're able to find cool things like when emotionality spikes, like with war and patriotism, and like what type of people leverage emotionality in their speeches. And I mean, I don't want to make political statements, but such and such people is what they find. Great. But the other thing that I also want to mention is if you look at these two papers, Wertevec and Glove, they have since 2013, almost 60,000 citations, which is just somewhat unimaginable. And almost all of these citations are for downstream-centered work. So it's really hard sometimes to find corpus-centered work under these mountains of citations. So that's one of the goals of this tutorial, to kind of surface some of that work and help to both build intuitions and best practices, but also to give you a starting point in your literature search as you go on to do more sophisticated analysis with word embeddings. And before we get started, I just want to make sure that we're sort of being very realistic about the connection between the training objective of word embeddings and models' stated capabilities, because machine learning is extremely susceptible to making magical promises and not sort of connecting that to what's actually happening. So let's talk about what we exactly mean by meaning. So what word embedding algorithms do is they take co-occurrence probabilities and convert them into cosine similarities. And in order to understand why that's encoding meaning, we're going to revisit the objective functions of Wertevec and Glove, and then we can refer back to those throughout the talk when we sort of are asking ourselves, should this work? Does this work? Why does this work? Looking back at the objective functions can always help us with something like that. So just note that Glove and Wertevec both work by building two representations for each word. A context word C for each word, which sort of represents the word in its role as the context for another word, and a focus vector V, and I just made up C and V. They're different in different places, but a focus word V when for just the word itself. And the final word embeddings are trained by kind of optimizing the matrix of context vectors as well as the matrix of focus vectors using the objective functions that we're going to see in the next slide. And I just want to apologize because the expressions are a little bit out of context, but I'm just kind of making a general point. So I think it's generally applicable. So just trust me and don't worry too much if it's a little bit not super rigorous. So, okay, well, let me go to the next slide. Okay, so in Wertevec, we represent conditional probability here of a particular context word given a focus word with this expression. And the thing to note here is that in the numerator, we have this exponential of a dot product between the context words vector and the focus words vector. So if two words co-occur, we want to maximize this and this entire fraction, and if they don't co-occur, we want to minimize this. And similarly, but also somewhat dissimilarly, if we look at the glove objective, it also has a dot product, and I'm going to sort of rearrange things to make them look a little bit similar. But here again, we're sort of, for every word in the corpus, minimizing this sum of squares. And here as well, we have a dot product between a context vector and a focus vector. And this term here is the co-occurrence count of the context word and the focus word. So the more often things co-occur, the higher this term is, and that's the higher that the dot product needs to be. And of course, also the less often they co-occur, the less often we want this, the lower we want this dot product to be. So that's basically the takeaway. This dot product is high for co-occurring words and low for non-co-occurring words. And I'm sorry, this is a lot of terms, so I might pause and just make sure that that was clear. Great, okay. So just to put all these things together with how we expect multiple words to interact, and I'm just recapping this to have it all down in one place. Sometimes I forget. It's nice to be able to like go back to having it written down. So both in glove and word2vec, we're maximizing the dot product for all words C occurring in the context of a word V. So suppose you have two words V and V prime, and they both appear near the same words, some C1 to Cn. We're optimizing distances to similar sets of context words. So they're optimized with similar constraints, which makes them similar in space. So words appearing in similar contexts are going to have similar vectors. So that's sort of the entire logic behind why these things work. Great. But then when we also look at this from sort of a theoretical perspective of the distributional hypothesis, this is something that basically almost all of modern NLP is built on, the idea that words that occur in similar contexts tend to have similar meanings. So if we accept this hypothesis and we say similar contexts occur with words with similar meanings, and on our previous slide, as we showed, similar contexts correspond to similar vectors, words with similar meanings are going to have similar vectors. So yep, that's all. I just wanted to make sure that we said that explicitly. Great. So I'm going to just move right on to the next section, which is word embedding analogies. And you probably are already familiar with this, because even if you weren't doing NLP in 2013, it got press even outside NLP. People were really excited that you could do this kind of math on vectors. And the idea was basically that if you had a vector for king and you had a vector for queen, the distance between the vector difference between those two encoded some kind of like masculinity, femininity shift. And it was shown that that could be replicated to show that you could shift words like man to woman, brother to sister using the same shift. And people were very excited about this constant offset. And the interesting thing is for word2vec, this was a totally emergent property. Like we saw the objective and it was just about like, oh, nearest neighbors, they co-occur, and working on the cosine similarity between those two. So this was like kind of unexpected. For glove, it was a little bit more designed, so I don't want to like totally go into it, but I did want to mention that people were surprised at the time. Great. So when we talk about the analogy task, that was actually used to demonstrate that analogies worked back in like 2013. Sorry about these random letters. There was like 19,000 questions kind of with this format. So city, country, or like masculine, feminine, or present tense, past tense. And the idea was that you could take a, sorry, I realize I'm looking at the wrong slides. Okay, all set. You could take the distance between the A and the A prime vector, and that would encode like a country capital relation or a masculine feminine relation, etc. And then you could just add the masculine feminine relation to a different masculine item, and that would get you to its equivalent feminine word. So you predict the word B prime by calculating B plus the vector difference of A prime and A, and then find its nearest neighbor. So unfortunately, there were results that came out since then that have been far less publicized that show that this isn't kind of that these results are a little bit misleading and don't fully explain what's happening. So you might imagine from the way that things are publicized that the like vector sum that you calculate lands like squarely in the perfect neighborhood of like the B prime word. But that's not always exactly what's happening, because if you look at, for example, the words flying and flew, they occur in a lot of the same context. So they're very close together in vector space. And what it turned out to be was that A prime minus A turns out to be very, very small a lot of the time. And the reason this wasn't something that was particularly noticed at the start was that the way results were calculated excluded B, A prime, and A as candidates. But it turns out that the word B, so let me just go back, sorry. Ooh. So the word B, such as like swimming, is often actually the closest neighbor of B plus A prime minus A, because A prime minus A is so small. And this was shown very emphatically by a paper that I really like in 2016 by Tal Linzen. And I sorry to throw a bunch of numbers here, but I think they're really interesting. So on the left side, what we have is a list of all the different categories of analogies. And if you just calculate B plus A prime minus A and look at which out of these 4 vectors or any other vector is nearest to it, it turns out that usually it's B. And because it was excluded, it didn't really affect the results. Sometimes it's B prime. It definitely works sometimes. But then the other thing that you can look at is these are the scores if you sort of score them the original way. But once you start including A, B, and A prime as possible wrong answers, suddenly your scores drop. So the original score is here. And then allowing these wrong answers, the scores are here. And you can see that the score drops everywhere. And it turns out also that like for some examples, like plurals, the two, a word and its plural are so close together that B prime is always just like the nearest neighbor of B. So you get like very high accuracy that way. So it's a little disappointing. But what this really just means is that performance on the analogy task can be explained by other phenomena like proximity rather than the existence of a constant offset. And this doesn't mean that there's no linear substructure in these word embeddings, just that what the analogy tests in and of themselves are testing doesn't prove that it exists. So that's fine. But then after that paper, there was also people talking about so the Google analogy dataset measured performance on 9 different categories that we saw. There was another paper that introduced 40 relations. And a lot of these relations were actually substantially more difficult than the original analogy. So things like animals to the sound that they make, or a thing to the color it typically is, or part-whole relations. And there was another paper actually much more recently that shows that you can sort of mathematically predict which sets of word pairs are successful as analogies. So they're kind of able to show that, you know, maybe capital country tends to land in a place in the word embeddings that make it more apt for analogical reasoning than like plurals. So the takeaway here is just that some analogy tasks are easier than others, and some relations are better suited to vector analogies than others. So, you know, if you have a particular social relation of interest that you want to represent as a semantic offset, it may or may not be well suited to representation by analogy, and that's something that you can check. And actually, speaking of social relations of interest, I want to also talk about semantic projection. This is something that you might have come across. Basically, the idea is that within your vector space, you build a semantic dimension based on antonyms, like small on one end and big, large, huge on the other end. And when you take different words in the space, those words' positions correspond to its qualities on that axis. And it's a lot of times this type of work is pitched saying like, analogies work, so this should work. And so I do want to address, like, how is this affected by the findings about analogies? And I think it's okay because, like, analogies don't actually need to hold perfectly. You don't need to actually have a perfect parallelogram for this to work. The requirement is much less stringent. So the thing that I would recommend is to use like kind of a litmus test for this type of work. And so we're going to look at the Colab notebook that I have real quick, and that will kind of explain it. Okay, I'm going to switch to Colab notebook. Let me know if anything is difficult to follow, because the Colab notebook hates me, sorry to say. This is all code just to reproduce the some of the plots that I put in the presentation earlier, so we're just going to skip over it. So here's a litmus test for semantic projection, and you can download the vectors that I'm using, but I'm not going to download them right now because everything's very slow. So I got these from Kozlowski et al. 2019. They're basically a set of antonyms. So there's like employer, employee, and owner, worker, and they're supposed to represent like an employment direction. And the idea is when you sum up all of the employers and you sum up all the employees and you take their difference, it gives you kind of a general vector that goes from employee to the employer direction. And as we said, that relation may or may not be well represented by analogy. So how do you sort of test and make sure? So I'm going to suggest that we, first of all, load some embeddings for different decades. So this is a corpus of historical American English that's actually from Hamilton et al. 2016. That's also cited in the slides. But I'm just sort of grabbing the embeddings here. And then we're sort of going over all the different antonym pairs, which here are those employer-employee pairs, and holding out one pair at a time. We grab out the rest of the pairs and create a positive vector from the positive pairs and a negative vector, a positive vector from the positive antonyms and a negative vector from the negative antonyms, which gives us sort of the main differential vector. And then what we would do is take the cosines of positive vectors of the positive antonyms with the difference vector, as well as the cosines of negative antonyms with the difference vector. And what we want to see here is the positive. So in this case, the employer word should be more aligned with the positive end of the employer-employee dimension. So that should have a higher cosine, and the employer, why did I pick these words? They're so hard to say. The employer should be aligned with the employer, and then the employee should be aligned with the employee end. So I've plotted these real quick for, I guess this is currently 1970. And what we find is the employer cosine with the dimension is on the x-axis and the employee cosine is on the y-axis. And we find that there's a couple of cases where there's overlapping, I'm sorry, but proprietor employee and director employee sort of don't quite make it there. They're a little bit sort of on top of each other, and they're not sort of, the employer word is not distinctly more related to the employer end of the dimension. And I think that's sort of not terrible, because we could expect that, you know, certain words might have different connotations in different years. They might not be the ideal sort of words to be using for this differential in this decade. But on the other hand, if these words are so close together, like proprietor and employee are sort of not distinguishable, it sort of raises the question about, like, if words that we know have this employer-employee relation aren't necessarily correctly aligned, like how much can we trust our measurements of, you know, the alignment of top hat versus baseball cap on the same dimension? And I think that this is definitely something that's like manageable. You can sort of try running this with different years. Like, I don't know, you can try 1910 and you might get, you know, foreman laborers, or there's just like sometimes one or two words end up at the wrong place. And it just means that you can use this to refine your set of adjectives to ones that you feel pretty confident work across all the contexts that you want to test in. Yeah, so don't despair. Analogies just don't quite work in the way that we sometimes talk about how they work, but there's still something in there, so don't worry. Great. Are there any questions about the analogy section before I move on? Or the code, sorry, the code was a little bit weird.
I just have a quick question, Neha. In that graph in the code that you're showing us, so is below the y equals x axis, those are pairs of words that are sort of
Yeah,
right
these are
direction.
pairs of words where the positive, the employer word had a higher cosine with the employer-employee dimension than the negative word.
Gotcha.
This entire sort of research direction is really a mouthful, and I apologize.
Yeah, no worries. And then so above the y equals x line.
Yeah, so above
confirm.
like the negative employer word, above the employee word is aligned with the employer end, which is not what we want.
Thanks.
Yeah. Great. Okay. So now I get to talk to you about some of my favorite things like polysemy and other shenanigans in lexical semantics. I'm so excited that I get to do this. Okay. So here's a random Reddit post that I just picked up. And interestingly, like for us as humans, it's very clear like which meaning of these words is applicable, even though each of these words can be used in multiple senses. And you might be familiar with people sort of saying like, oh, a bank could be the side of a river, or it could be a financial institution. But I think, you know, while that's sort of like a very canonical example of polysemy, just even the existence of like homonyms is just so prevalent that we don't even realize it. And so for example, here, the word hands could in a corpus like occur in a lot of different contexts with a lot of different, slightly different meanings. So could the word red, front, light, bulb, all of them. And, you know, besides sort of the tiny distinctions between like the theory of which of these are true polysemous words and which are homonyms, none of those really matter for us, because for us, different occurrences of the same string might have different meanings, but we're collapsing them all into the same vector. So we're going to talk about what this means for the model and then what it's going to mean for you. If you look at a model like this, going back to how we discussed kind of the focus vector and the context vector, a word V could have multiple sets of context vectors that are not super related to each other. So maybe the word mouse is related to console, printer, keyboard, but it's also related to like tail and pet and cow. And what happens here is you have two sets of constraints that are both sort of, due to this dot product, dragging the vector for mouse in two different directions. And what happens as a consequence of that is words like keyboard and cow are also getting pulled together, and this can result in some sort of counterintuitive nearest neighbors. So question, is this going to happen to you when you are doing your own research? So maybe not. Maybe if you're using like a very specific corpus, multiple senses aren't going to be present and it's not a problem. Or if you're interested in like the primary sense and most of the contexts are of the sense that you care about, also not a problem. But one thing that does happen is suppose you care about a sense that is overshadowed by a more prevalent sense. So earlier I was trying to make vectors and look at rich versus poor in Wikipedia, but when I looked at the nearest neighbors of rich, I was getting like vibrant, tangy, lively, fertile, which was really weird and not what I wanted. So yeah, don't panic if this happens to you. Actually, a lot of really clever work went into trying to fix this between like 2014 and 2018. So people did unsupervised sense clustering, they did dictionary methods. But the thing is, like, unlike these valiant researchers, we have the benefit of living in the future, and we can use BERT-based approaches. And there's actually a lot of really cool work because contextual embeddings like BERT and Elmo already account for different senses by design because embeddings are connected to a particular occurrence. So I guess just the takeaway that I want to say is like polysemy is a thing that happens, but it may or may not affect you. But if you find that it does, there's contextual embeddings can help you to tackle it. So don't worry. Okay, and now I get to talk about another thing that I find really fun, which is antonyms. So it turns out that they're not as easy to sort of describe as like the opposites that we talk about in kindergarten. Like perfect antonyms aren't easy to come by, like tall and short and I don't know, fast and slow. So for example, Republican is the opposite of Democrat, but it's substantially more similar to Democrat than like most things like stapler or mitosis or carelessly or lumen. I just like naming words. But yeah, so those two words are actually quite similar. And antonyms are actually often nearest neighbors in vector space. And to get a sense of the extremely counterintuitive vector space, I would suggest playing this game called Semantle. It's like Wordle, but you find like, you try to find a word in word2vec space and it's impossible. It will definitely make you cry because like words that you don't think should be together will be together because of weird senses they share or because of like antonyms, and it's really weird. So just be prepared for weird things to happen because words are weird. So it was found in 2014 that windows of size 5 or larger when you're training your embeddings contain topical content. So, but smaller words contain information about the focus word itself. So you can imagine that like Republicans and Democrats are sort of within the realm of topical words for each other. So actually, if you look at antonyms and their rank for how close they are in nearest neighbors, they can actually be quite close. So these are results for the employer-employee antonym set, and sort of there's kind of a lot going on here, but if you look on the right side, there are plenty of times that the like whether you use a small window or a large window, the opposite of the word tends to be pretty close by in space. So I just want to say that the takeaway from here is that antonyms are very similar, and where they end up with respect to each other in the space depends on a lot of factors. So if you're relying on the geometry of antonyms in your work, it's definitely worth paying attention to this and looking into it more closely. One last thing I want to say about antonyms. This is a bit of a controversial example, but okay, wait, let me start with the definition. So one definition of antonyms are two words that differ along one dimension of meanings, maybe occupying opposite poles, but are identical in all other dimensions. So controversial example that I got from a real paper is progressive being the opposite of redneck. So, I mean, are those antonyms? Personally, I would say like no, because they're dissimilar with respect to political orientation, but they're also dissimilar with respect to connotations. So that's sort of two axes of dissimilarity. And I guess the thing that I want to sort of highlight here is if you were to use this pair, you're sort of nudging the Democrat end of your differential vector into complementary territory and the Republican end into sort of derogatory territory. And you could amplify this bias, and it might then look as if the data support more unkind views of Republicans. So I think just sort of keep in mind that antonyms are very tricky, and make sure that you're thoughtful about them as you're using them. And I think this is actually a really good guiding principle of like being identical in all but one dimension. Great, okay. So are there any questions about polysemy or antonyms before I move to the next part?
I guess a simple question is, are antonyms ever used in like the analogy task we were talking about earlier, or would you consider those like completely separate?
They aren't used in the particular, in like the Google set. I think there are some, and okay, so there are a lot of different types of antonyms. So there are antonyms like, you know, what's a good word? Like a verb and then that verb. Why can't I think of a single verb that starts with un? But those types of antonyms are in the BATS test, but I don't think they're in the Google test set. But for those types of antonyms, because they're sort of so close morphologically, it does work like somewhat pretty okay, if I remember correctly. Sorry, now I really want to think of a verb that starts with un. Enroll and unenroll, maybe, yeah. So those could be considered antonyms. But I guess I was talking more about noun antonyms here because that's what people are using in semantic projection research. And those are not super prevalent in the analogy tasks. Great. Okay, so finally, I want to talk about the stability of word embeddings. All the results in this section are from a really excellent paper by Antoniak and Mimno, 2018. And just as a warning, the main takeaway from this paper is you need to run a lot of replicates of your experiments training word vectors, which we obviously cannot do in a 1 hour window. So please refer to this excellent paper. I have not run the thousands of experiments that they ran. So I'm going to refer back to them a lot, but we will look at code and not run it. So one thing to notice is that the training of word embeddings is stochastic. So unlike some deterministic methods where you're just sort of counting co-occurrences, the final value of the vectors depend on like a lot of different things. So some of them sort of make more sense, like the precise combination of documents you use to train your model, sometimes the order in which the documents appear, and also things like, say, pre-processing and the random seed, which, you know, are still somewhat within your control. But then if you use multi-threaded training, the exact values also depend on kind of the order in which threads are scheduled, which is totally out of your control. So there's a lot of different sources of randomness. And first, we're going to just talk a little bit about how much different sources of randomness can affect your embeddings. So let's look at what happens when you change the random seed into otherwise identical training of the same vectors. So what I did here was I took a Ask Science corpus and computed cosine similarities between pairs of kind of topic words from that data set. And what I found was that there are, you know, there's sort of some jitter. They're not quite the exact same cosine between model 1 and model 2, even though the only difference is the random seed. And on the one hand, it's like, well, that's fine. That's only like, it turns out on average a 2% difference. But it's also kind of not fine because like these are the exact same set of contexts. So it seems really weird to sort of say, oh, V1 is more like bacteria is more different from plant here than there based on the exact same evidence. So the takeaway here is that the exact cosine value doesn't actually have an intrinsic meaning. The cosine value really only has meaning with respect to other cosines in the same space. So if you remember when we talked about objectives, all we were doing was making sure that the dot products were higher when the words co-occurred and lower when they didn't co-occur. So at this point, you might be a little bit annoyed because first she said analogies don't work and now she's saying cosines don't work. So it's not that bad. I'm sorry that I made it sound very dramatic, but suppose you have two different training settings, A and B, and you know that could be two corpora, two random seeds, two different runs of the same training. So what can you actually compare with cosine? So first of all, you can compare, suppose you have cat and dog and you want to compare that cosine with cat and tree in the same set of embeddings. That's perfect. That's the canonical example. It's wonderful. Exactly what we trained for. Go for it. Suppose you want to compare cat and dog with like tree and car. I don't know. That's a little bit less well defined because you know, they're in the same space. And even though we didn't directly optimize for them the way that we're like, okay, cat is closer to the things that it's closer to and further from the things it's further from, all these four words, cat and dog and car and tree, have words in common, and those words have words in common. So there's in some way those things are mediated, but it's still sort of a little bit sketchy. I don't know. I wouldn't do it if I could avoid it. One thing that you can't do is compare the cosine between cat and dog in training setting A with cat and dog in training setting B. Because, for example, cat and dog could be nearest neighbors with a 0.9 cosine in setting A, but just land in a more sparse area in setting B and have a cosine value of 0.4, but they're still closer to each other than any other word. So that's sort of the thing that you want to pay more attention to, which is who is closer than what and not kind of the exact number, but you can compare who is closer to what with cosines in the same training set. And this almost goes without saying, but the worst thing we can ever do is compare cosines between two vectors that were trained separately. We don't know what those dimensions mean. It's something latent. It's not guaranteed. So yeah, let's never do that. Great. So one way to mitigate this instability over the different cosines is to run multiple runs and report averages. But another thing to remember when we're sort of deciding how to run multiple runs is that word embeddings as we talked about in corpus-centered research, are a representation of the author's mental model. And they're really only a sample of the author's mental model. We don't have sort of every possible document that an author could have written. And this can introduce error, but the question is sort of how much error? And the answer to that question is surprisingly a lot. I'm just going to show you some results from the Antoniak and Mimno paper because I didn't run these things myself. So what they're showing here is the results of 50 different models trained on Ask Science data. And they show the cosine results of, they show the cosine values of the word marijuana with its most similar words using different methods. So the left one is word2vec and the right one is glove. And as you can see, bootstrapping, which involves sort of dropping out some of the documents in each run, actually results in a huge variance in cosine values. So that kind of reinforces the fact that we really need to be reporting averages, because this is quite a large distance in which to land. I also want to mention that they did investigate whether shuffling the documents, which is kind of the green line, also affected variance in cosine similarity, and it didn't quite as much as bootstrapping. So don't worry too much about that, but account for it because you can, because you're going to, now that you've seen these plots, you're going to run 50 training runs. So cool. Great. So the idea behind bootstrapping is you run multiple instantiations of the same model and then you report averages rather than raw values. And the way that we do that is to draw documents with replacement. And I want to say we'll look at this code in the Colab notebook, but I think the real beauty of this paper is that the idea is super, super simple. I think the main contribution is the insight and the very rigorous execution. So even though I'm going to show you the code, you're going to be like, this is 2 lines of code, but it's 2 very important lines. And again, please read this paper. It's a very good paper. Yeah, okay. I'm just going to skip over the rank stuff. Okay. So if we go here, basically, so what I've done is I have this function to build a word2vec model with GenSim, and I'm just sort of giving it a set of sentences and a random seed that you might want to sort of send it off with different random seeds. But I want to mention that there's sort of 2 obvious ways that you can get random results with GenSim. One is by setting the random seed, and one is by just the fact that num workers is greater than 1. Setting num workers greater than 1 will give you deterministic results, which is nice if you want everything to be super, super, super reproducible. But it takes much longer to run. So that's sort of the trade-off that you're making. But if you do decide that you want a deterministic, then setting the random seed, which is great, not set here. Awesome. Good job, Neha. But you can send it in as like a parameter to this word2vec constructor. Setting the random seed will give you sort of different random runs of the same training. So basically, the way that I had to prepare my data for bootstrapping is to just sort of have every different document separately in a dictionary. And this can kind of be annoying because like what I really want to do is just put all those sentences into one big text file and just read it in. And this is like slightly more work, but it's definitely worth it. So the idea is that you might put things into sort of a dictionary where you can refer to different documents separately. And then what we're going to do is we're going to pick out keys from this dictionary that tell us which documents to put into our corpus. And that's going to let us do bootstrapping, which, as we said, is important. So, okay, I'm going to skip over pre-processing, whatever. You can, of course, refer to it, but it's just boring. And this was just to make the plot, which also you can look at if you want to see, but it doesn't really matter. Right, so I wanted to show, yeah, so this whole like sampling with replacement in Python is like very, very simple. You're just sort of importing random and then you run random.choices with sort of k equal to the same number as like the number of documents in your list. So if you do it on a range of 0 to 10, you might get something like this. And we have sort of 2 in here twice and 5 in here twice, and we don't have a 1. And that's sort of exactly what we want for the kind of sampling with replacement for bootstrapping. And then after that, it's just it's very simple. You just run as many bootstrap versions as you care to run. You select your keys by using random.choices, and you just keep on creating models. And then after you do that, you can aggregate all the nearest neighbors or the cosines from different models so that you can report an aggregate. But yeah, it's a very simple but very powerful idea. And that's basically all there is to it code-wise. Are there any questions about this? Sorry, I know I kind of ran through it very quickly. Okay. So yay, we are able to mitigate this. I wanted to also mention, like, why do we draw documents with replacement rather than drawing sentences with replacement, which would be so much easier? I want to just point out that a word's context in a document are likely to be very similar to each other. So this is sometimes called a one sense per discourse concept. So if you think about our earlier example, it's very unlikely that in a certain document you're going to get a light bulb and the tulip bulb context. So if you sample just sentences rather than sampling documents, what you're simulating is just sort of shorter documents rather than different documents that weren't in your corpus. So even though this is a little bit more work and you will get slightly larger variance numbers that might feel a little bit disappointing, it's worth it because it's definitely more rigorous and it's like the right way to approach this. But yeah, so that's kind of what I have for stability that is sometimes called instability in the slides because I didn't change them all. I have a couple of parting thoughts that I think are just nice to have written down somewhere. So people are often asking, like, why do we use cosine versus Euclidean distance? And I wanted to just just write it down. So there's a couple of reasons to prefer cosine. So first of all, if you normalize your vectors and you rank nearest neighbors, which is definitely the recommended way to analyze your results anyway, the ordering over nearest neighbors is the same using Euclidean distance or cosine. So it's it doesn't matter, it doesn't make a difference. But where it does make a difference is if you're using cosine distance, you can use a dot product to calculate a lot of them at the same time, and that really speeds up your evaluation. Just remember to normalize everything first. And then, because basically if you just do a dot product of two normalized vectors, it's equivalent to a cosine because you don't have to divide by the magnitude. And the other thing is magnitude is kind of hard to interpret. If you remember from when we talked about the objectives, that was not something that we were particularly optimizing for. There's definitely work on interpreting what magnitude means, but it's sort of out of scope for this talk. And I think, you can actually go a very long way without using Euclidean distance. So I would just strongly recommend sticking to cosine because it has so many advantages. The other parting thought that I had was I just wanted to make sure if you're using word embeddings that you keep in mind bias in word embeddings. It's sort of the flip side of the fact that corpora reflects the author's mental models. Word embeddings and other machine learning models tend to reproduce hegemonic viewpoints because who is producing these texts that we study, whether it's sort of Reddit or news or, I don't know, old-timey something. But yeah, so machine learning can reify like the viewpoints that are produced in text. So it's just like, although taking a look at these references that have sort of explained in detail what the dangers are of bias in word embeddings. So that's kind of all I have actually. Thank you so much. I talked way faster than I planned. I apologize for that, but I'm going to put everything up here on my GitHub to refer to later. And thanks for your time and attention. And let me know if you have any questions. Great, thanks so much.
Great, thank you so much, Neha. We do have one question in the chat, and there's a lot of claps as well for you. This was a really great tutorial as well. Thanks for putting all of this together. So we have a question, can we use k-nearest neighbors for classification of in class or out of class? If you want to unmute and clarify the question, feel free to.
Yeah, could you say more about what type of classes you're thinking of?
Hi, my name is Pratima. Yeah, I'm enjoying the session and really informative. So I just wanted to know whether a word belongs to a particular group of a class. Like if we are trying to group into one, clusters like books, reading, pen, pencil, and these things. And suddenly some other thing comes that similar to that, but it doesn't belong to that particular group. So for that, can we use k-nearest neighbor, or we can go for some other classification?
Sorry, I was muted. Yeah, I guess I don't totally understand sort of the overall goal. Like you're sort of training some like embeddings, and then you have a certain set of words and you want to classify the extent to which the word embeddings put a certain type of words in the same class, in the same class, in the same neighborhood. So I think you absolutely could use k-nearest neighbor for sort of classification, but if you're specifically, I mean, do you mean as a way to diagnose sort of interlopers that are in the wrong neighborhood? Like, I think that definitely makes sense.
Okay.
Like if you already sort of know the sets of words that you expect to occur together, like definitely. I mean, I don't know if that's sort of the goal of the task.
Cool. I had a quick question, I guess. So you had that point about not comparing cosine similarity between like different sets of word embeddings, which totally makes sense. I don't know what your thoughts are about, instead of doing cosine similarity, doing like sets of nearest neighbors. I know that's sort of a metric that's been used in some sort of word embedding work, but I don't know if your thoughts on like how valid that is, or like if there's also problems with that.
I think that's amazing. And honestly, I didn't put it in because I didn't think I was going to end up talking this fast. But a lot of things, I think definitely comparing nearest neighbors is a really good way to get a sense of what's going on. And the really nice thing about that is you can also quantify differences in the sets of nearest neighbors. And the way to do that, I think I actually might have that in here somewhere. But like, yes, you can look at like a table and be like, oh, okay, here abortion is near like motherhood, and there abortion is near something. I can't use real political examples. But you can also look at the ranks of nearest neighbors and look at the way that the ranks change between different instantiations of word embeddings. And what I really like about that is it sort of gives you like a pretty clear like quantitative way to compare them, which sort of helps when you are comparing huge amounts of things. Both ranks, and there's a measure called Jacquard similarity that's sort of the intersection of the two sets of nearest neighbors divided by the union, or sort of the magnitudes of those two sets. Those are both really great, and they're also both in the Antoniak and Mimno paper, which I again strongly recommend.
Cool, thanks.
Great.
Any other questions from the audience? Yeah.
Is it okay if people also email you afterward? They might come up with questions
Oh,
later.
yeah, absolutely. I should put my email on there, but I put my Twitter for some reason. But you can also DM me on Twitter or email me, or yeah, any of those things. I think Katie linked my website, which has all those things on it. So yeah, and I mean, also, I'm kind of learning about social science, so I would love to chat with people and just, both like help with word embedding stuff and learn about what you're doing too. So definitely reach out. I would love that.
Great. Well, then we will move any other questions to Neha offline. Thank you everyone for participating today. Oh, and take 1 minute to fill out the post-tutorial survey, please.
Okay, looks like we have one more question.
Oh, here we go. Go ahead.
Yeah, so to answer the question here is, are there good tools or matrices for clustering sentences? I would say, again, we have the benefit of being in the future, and Bert or Roberta or, Cybert or whatever is appropriate for you produces excellent sentence embeddings. But if you really wanted to use your own, like your own embeddings that you trained on something that are particularly different from like BERT or SciBERT or whatever. I don't sort of have a reference for this just off the top of my head, but honestly, people have averaged vectors and found that that works great. Like just take the word embeddings and average them. Another thing you can do is sort of weight those averages by something called like TF-IDF, which is sort of how common those words are in your particular document. So it kind of makes the and those kinds of words less important. But yeah, averages and weighted averages definitely work really well if you can't use like some kind of contextual language model. Awesome, thank you, Katie.
Yeah, I'd build off of that and say there's this great paper by Sanjeev Arora and colleagues that does exactly what Neha is talking about. It's kind of like a weighted TF-IDF with some other like sort of dimensionality reduction thrown in there too. And it's a really, like, as the title says, a simple but tough to beat baseline for these static word embeddings. But Neha's point is also very good that we've sort of moved on in the NLP community, and then we have these contextual embeddings too.
Yeah, I think that is the paper that I read and internalized and was referring to. So thank you.
Okay, great. Now we are at time, and I think we will wrap up. So thank you once again, Neha. This was a fantastic tutorial and a really great contribution to the community.
Thanks so much.